Also participate in the night by coming up to the Queen's Domain playback Reast. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind, doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30pm local time. We'll see you soon. This is VK7HH.
Okay, this is VK7HH, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And thanks to Ben. I actually got a stream, Ben, so I'm not quite sure what's happening. Okay, I know exactly what's happening. Just bear with me. We'll go to make the stream public. Let me just, yes, okay. And we'll save that and publish it. Okay, there we go, Ben. That should be good now. Tonight we've got a pretty full night, actually. We've got a little bit about OmniRig and DigiRig, a little bit about an interesting unpowered, so non-motorised. Thank you, Hayden. Very good. And I've got Hayden VK7HH from HamRadio DX in the studio with all his camera gear and everything as well. So we've got a very full studio right at the moment. We've got, and then we move on to our second workshop on GNU radio, which bit more of a setup workshop than it is an actual doing workshop, but we will have one of the exercises that we won't that we'll be doing just to work through the interface for GNU radio. What I'm just going to do, and thank you Ben for the echo side of it. I've just dropped one of the microphones back. If you can let me know whether that echo has disappeared, that would be really, really good, because I have a feeling that there might be a little bit of a time difference between those two microphones that we've got sitting on the bench. So just let me know, Ben, via the chat channel or text whether that's resolved the issue. So what I thought I would do is we'll head to the PC. Okay, now on the PC, I've actually got. I was sent this particular website by a SOTA guy from the US. Who is Bruce, who is November 7 Romeo, and he sent me a link of the Monowalker Fatmate, which is a non-motorised platform, and you can see it there. Non-motorised platform, and you've got a harness that you can wear, that you can hook it to. You can fit a huge pack on the back here, as well as there's panniers that go on either side of the wheel. There is actually a brake on the wheel, a disc brake on the wheel that you control through the arms that you pull the thing along with. You can see here's some examples where people are using it. This is a rescue arrangement where they've got a carrier for somebody who's injured. You can see people walking here, and a few other. Oh, here it is, side on. So pneumatic tyre. So there's the harness that I was going to show. So it clips onto it. You can take that weight on your shoulders and around your midriff, very similar to a pack. So he sent this through, and he sent it through with the use of it being SOTA, because one of the rules in SOTA is you can only head up the mountain unmotorised and unassisted by any sort of motor. This enables you to carry a huge amount up the mountain. Now, I just have to say here, you need a reasonably flat and sort of non-rocky pathway to actually pull this up. But it's certainly an option for getting your gear up the mountain. So. It's called the Monowalker Fatmate. It's made by a German company, and I'll put the link in the presentation right up so that people can actually go to it if they want to have a bit more of a look. Okay, still has an echo. Let me just try something here, Ben. I'm just going to go across to the other microphone. So I'm now across on the other microphone. So just let me know whether that's resolved it or not. Hello to Anthony. It's a one wheel for luggage, yes, but one wheels are powered. So having someone in my family who has a one wheel, no difference. Okay, well I'm actually slightly at a miss as to what's going on here, so we might have to put up with that for the time being. But anyway, so the next thing I wanted to actually go through is we featured the DigiRig about 2 DATV nights ago. The DigiRig is a little interface. That contains both a audio codec and also a USB to serial port interface that enables you to connect to a radio and control the radio via CAT, and also the audio in and out from your rig. And then on the other side, you've just got a USB that comes out that goes to your controlling computer. And I actually said, I actually sent the arrangement to Denis Grisak, who is K0TX, who is the brains behind the DigiRig. And he came back with a few suggestions, which I think are great suggestions. The very first one that he talked about is the Windows sound settings should be moved to default from the DigiRig to the laptop speaker and microphone. And the reason you do that is then the actual sounds that the PC makes in relation to various things don't actually end up going through to either the radio or the computer, depending on which way you've set the sound system up. So he makes the comment: the system beeps and boops will not go to air, which is fantastic, and obviously won't affect any decodes, WSJT decodes. The other thing is you can rename the particular device to DigiRig. Instead of the default that it will come up with when it finds the DigiRig device, you can rename those devices to DigiRig. So whenever you plug the DigiRig in, it'll actually show in the device manager as DigiRig, which is really handy because if you've got multiple sound devices or multiple USB devices, you can actually get confused as to which one it is. So from that perspective, that's a really good suggestion. For RFI reasons, shorter cables between the DigiRig, shorter cables from the audio perspective between the DigiRig and the rig, and then you rely on a variable length USB cable to get to your computer. So you're not going to introduce any sort of RFI artifacts. Really good suggestion. And he made the comment, he said, try OmniRig as the intermediary software. So what I was going to show you is, if we go to here, when you plug in the DigiRig, if you go to Device Manager, you can pick up which COM port it's actually using, which in this case it is COM3, which is fantastic. So if we head down here, and I have actually installed OmniRig. Now OmniRig is free software. There's a wonderful little arrangement where you can contribute a coffee to the developer, so encourage that. When you open the OmniRig settings up, you see there's a little control panel comes up. You can control 2 rigs, and so I've set this up so that I've got the FT817. I know that it's on COM3, so I've selected COM3. The baud rate needs to match what the rig's set to, which it is in this particular case, and in most cases the rest of it you can leave as is. So you can also, with OmniRig, you can control 2 rigs, so you can set it up for, if you've got say a receive and a transmit type rig, if you're using that probably for like a satellite arrangement, you can set that up accordingly. Now the next thing is, I've set up VKCL, which is the Australian contesting from Mike, VK3AVV, and the way that you set it up, now that you've got OmniRig all set up for that particular rig, if you go into configuration, it goes off and it actually looks to see whether OmniRig's installed when you do use VKCL, which is a really nice thing. If it is installed, it actually comes up and says, this little box here which says Start OmniRig. So if you click on that, it'll go off and it's gone off and actually initiated OmniRig, and it says stop. So in this case, when you're doing your logging in the contesting, it will actually grab the settings that are on the radio and log them in as part of the logs for the particular contest. So the frequency, the mode, etc., all of that gets logged and read from the actual radio. So that takes care of that. Now, if it happens to be a digital contest, so WSJTX, I've also got installed on this particular PC, and you'll see it's starting up. This is the latest one. This is the latest RC. So release candidate number 4 for 2.4.0 expires on the 30th of May. And the way that you configure it is go into File and Settings, and then Radio, and you'll notice up here it says OmniRig, and if you look at the list of radios in WSJT, you will find there is OmniRig Rig 1 and OmniRig Rig 2 if you've got OmniRig actually running at the time. So we've got the 817 on Rig 1, we put it on Rig 1, and what we now find is we can, and just bear with me, because what I can do here, if we change to, this is now a picture of the 817, and if I change frequencies in WSJT, it's magically talking to the radio. So, as well as, if I then log that as a contest entry in VKCL, it will be picking up those frequencies and the mode that I'm actually using there as well. So, so you've got 2 bits of software, via OmniRig using via OmniRig and DigiRig, controlling the rig in both directions for the two applications. So that's how you set it up for to use two applications. It can be two rigs as well if you really want to, but two applications with the same rig. So yeah, that's DigiRig, and actually setting it up for a couple of applications. Set up the first one, which is your contesting software, then set up your actual digital software, and it's the second bit of application that you actually the second application that you actually the second application that you actually set up looking at OmniRig. It's not looking at the actual rig. The first one is looking at the rig, and then the second one is looking at OmniRig, and that takes care of the sharing of the COM ports. So there you go. Maybe within OBS. Thank you, Tony. Desktop audio. Okay. I'm not sure I can fix that right now, but anyway, we'll see how we go. So, and the other thing I just want to mention is you don't. I didn't have to do anything in OmniRig. There are a whole bucket load of rig dot, and it's the rig type, so FT817 or whatever .ini files. I did not have to use or configure anything in that ini file. It worked out of the box. I think if you've probably got two rigs and you're trying to set up different streams and that sort of thing, you may have to play a little bit with the ini files. But I found it worked with VKCL and WSJT out of the box. Didn't have to do anything. So yeah, that's just worked. Which is really, really nice. So yeah. Now, okay. The second bit of our night is we started off last week with the very first bits of information out of the microwave update for 2019 GNU Radio workshop, and I gave the links to this. This is available in PDF on the North Texas Microwave Society website, so I'll put that up again. And thanks again to Rex in pointing me to this. Rex actually did this workshop over in the States in 2019 when he was there. And just to recap, GNU Radio, open source software. It is open source radio development software. Based on Python and C++, you do not have to know either of those languages to be able to use GNU Radio, so don't worry about that. It uses, just so you know, the Python, the way it uses Python is for the interconnects and the graphical user interface that we'll go into in a sec, and then it uses C++ for, well, everything else, which is all of the interconnects and all of the high-speed software processing that it has to do. So that's how it uses the two of those. It all gets represented on a what they call a flow graph. And what I will actually do, here, because I had to jury rig this last time because we actually couldn't get into the studio. But what we can do is we'll head over to the PC. That looks a bit crappy on there, but it's actually, that's that monitor, it's not the what goes out. Go down. I showed you this last time. Once you've installed GNU Radio, that particular version installs both GNU Radio 3.8 and 3.7. You're looking for GNU Radio Companion. We'll open that up so you can see what it goes through. It goes through a little bit of setup. So the first time you actually do this, it does a bit of a different setup and a few things, and then all of a sudden it opens up your flowchart arrangements. And working on it. Oh, there we go. Goes through, processes all the blocks, and then opens up the DDD, flow chart, so the flow graph workspace. So, getting there. Here we go. And it's like, okay, so what we're looking at here is the flow graph for exercise. We'll go back to exercise 1. This is the one we did the other day. You'll notice that there is a little options box that we talked about. So this is what language it's using, what generation options it's using, and all sorts of things. There is a variable in here which it defaults when it starts up, which is the sample rate. The default sample rate for each of these blocks that we're going to be using, and that default sample rate is 32k samples per second. We came up with a signal source block, which is here. You can see the frequency is 4k, it's got an amplitude setting. Sample rate, surprise, surprise, is at 32k, and the waveform is cosine. It goes from this block into a converter block, which is a float to complex. And last time we went through, you'll notice some of these are orange, these little connectors, and some of them are blue. Now, the orange connectors are of type real, and the blue connectors are of type complex. Now, what does a complex connector type mean? A complex connector type means that you have both your I and Q signals, so the flow of data between blue blocks involves pairs of the I, which is the in-phase signal, and the Q, which is the quadrature signal, and there are pairs that actually get pairs of data that actually get transferred. So it's your I and Q signals on those blue lines, whereas the float here is just a single data stream. One value gets transferred, and what this block does is convert it from one float value into an I and Q. Now, we talked about a throttle last time. Now, GNU Radio, when you start placing these blocks together in certain things, comes up with little warnings every so often and says, oh, no, hang on, you need to actually install a throttle in here. And it gives you an idea about where, because if you've got elements where the source or the sink, it can be either, but the source or the sink has a data flow coming out of it or going to it, it has the capacity to actually basically take the CPU to 100%, almost instantaneously, and so you actually need to throttle back what these blocks use. And the throttle just means that the flow of data from this block to this block is throttled back to 32k, and you won't have a problem with how much CPU it actually uses. And then it goes into a block called a frequency sync. So this is QuickTime graphical user interface frequency sync. Now, I also talked about last time that there was this concept of there being sources and sinks. Now, sources and sinks. So sources are sources into the flow graph. So it's things like, it can be a radio, it can be an RTL SDR, it can be a TCP or UDP stream, so you can actually get something over the network. It can be a sound card, it can be a frequency generator, in this case it's a signal source on this particular flowchart. And a sink is the opposite to that. So a sink is actually, it removes samples out of your flow graph. And surprisingly, the source is at the beginning and the sink is at the end, and that's the sort of flow that you would expect. Now, sinks can be, again, they can be a radio, they can be a sound card, so you're actually getting I don't know, an audio frequency out of your flow graph. It can be a TCP stream, it can be all sorts of things. So that's the sort of concepts between a sink and a source. There's lots and lots, and I showed last time that there are core blocks here, down the side here, audio, Boolean operators, there's coding, there's control ports, there's digital television, there is Fourier analysis, there is GUI widgets, there's instrumentation, there's all sorts of stuff here. These are all blocks that you can actually use and incorporate into your flowchart. Now, a lot of these are what they call transformational blocks. So it takes the stream, it modifies it in some way, or changes the flow through, and then it gives you something out the other side. And a good example from that'll be understood probably within radio is something like a low-pass filter. So a low-pass filter literally filters, you put a frequency in one side and it cuts off at a particular frequency that it's designed for, and it lets through everything below that frequency, but filters out everything above that frequency. And there can be high-pass filters and band-pass filters and all sorts of things. And so that block enables you to configure that particular filter, and that's called a transformational block. But it can also be, I don't know, a demodulator, it can be FM demodulator, a delay block, a throttle can also be considered to be a transformational block, etc., etc. So, now another concept, and I'm sorry, this particular second workshop is a little bit more about understanding the concepts within GNU radio, and then we'll start putting some things together. On a lot of these blocks, if you click on the block, and you can see it comes up with a little blue line around it, and I just point at the output of this particular block, if I use the arrow up and arrow down keys on here, you'll notice that it changes colour. And if I change it to a particular colour, the connector between those two blocks actually goes red. And what that means is that it actually won't work. So it's actually telling you that, okay, you need to connect like outputs to like inputs. In this case, I've changed it to a float output of here, and it goes to a float input, and magically you get a black connector back again. There are all sorts of connectors, and if we go up to help and types, you can see that there is a complex float 64, 32, there is a complex integer 64, 32 and 16, there's a complex integer 8, there's a float 64 and float 32, there is integer 64s and integer 32s and 16s and 8s, there are bits which are unpacked bytes, asynchronous messages, bus connections and wildcard. And so these are all the different types that potentially a block can include and can actually output or input to, and you need to be aware that like outputs to like inputs, and where you can't actually change the output or the input through your little arrow up and arrow down keys, you actually need to employ things like the converter blocks, and here's a classic example of a converter block, which is it changes the float value coming in here to a complex value coming in here. So this is a single stream, changes it to a paired stream, a complex output of the I and Q signals. So it's a bit of a concept in GNU Radio Companion where you have to make sure that the outputs match the inputs and vice versa, so it actually flows. And when they don't match, they go red. Either the connector goes red, or the actual block name goes red when it actually can't do what you're asking it to do. So it's a really good way of knowing how to properly put things together within GNU Radio. So, now, complex versus real streams. Okay, so I talked about a complex stream being a paired value of an I and a Q. So the I is the in-phase signal and the Q is the quadrature signal. If you've done any sort of processing with software-defined radios, you'll find that there is an I and Q stream that you actually need to do something with. So a complex signal is just contains a paired value of the I value and the Q value as well. So that's when they talk about a complex flow or a complex data stream, that's what we're talking about. In a real stream or a float stream, what we're talking about is a single value. It's a single floating point number of whatever size you actually select here, and there are 64, 32, 16 and 8 in that particular case. So you've just got to make sure that they actually match, and that's number of bits. So you have to be aware that if you're sampling at a particular rate, you have to have a certain number of bits to be able to then represent the waveform or the frequency that you're actually trying to move from one block to another. Now, what I was going to try and do here is a bit of a, and this is probably going to confuse more than it's going to help. So I'm not sure this is going to work or not. Just let me. We'll put this. Just wanted to show how we represent an actual complex number. So if we go, okay, now let's zoom out here a little bit. Okay, this is the workbook that comes with it, and complex notation. We talk about a single frequency can be represented by this scary formula here, and you can see they represent the I value, the Q value, and then there is an amplitude in here, and that's how you actually can break down a single frequency into its constituent frequencies. So this is the Fourier transform type of transformation that we're talking about here. And the way that they actually represent that is in what they call a constellation diagram, which is this one here. So anything on this side is positive, anything on this side is positive, negative and negative, and then you've got the vector value, if you like. So on one axis there is the Q in the imaginary number, and then the other axis is the real number, and where that then sits based on its amplitude from the centre is how you represent that number. Now the key thing here is you've got quarters in here which are negative. So you can have this concept of there being a negative frequency and there being a positive frequency. So, and I'll show that when we actually run the exercise, exercise 1, and then I'll magically show you how we get that back to a single frequency. So that's how we represent a complex notation. There is a whole lot of mathematics behind that, which I am certainly not the right person to go into this. But it's a way of representing those numbers that actually involve a vector. So now let's go back to exercise 1. So just let me check that I've got everything. Yeah, and so complex number describes a vector on a complex plane, which is what that diagram actually talks about. And a real number has so there isn't a vector involved with a real number, only exists on a real axis. Therefore, there's no concept of there being a positive or negative frequency, it's both frequencies at the same time. And that's probably a good way of, if we run this, and I talked about the ways of running. Once you've got a diagram in here that you've got no red in connectors and it's doing all of the right transformations, you can go up here and this little forward symbol up here says execute the flow graph. So go away and you'll notice down here this is our little messaging area, and it's going ahead and it's compiled the flow graph, and this is what we're looking at here. I'll just pull this down. This QuickTime GUI frequency sync, this is the output from that particular block. And guess what? We've got a minus 4 kilohertz signal and a positive 4 kilohertz signal. Because we've got the signal source at 4 kilohertz, the amplitude at 1, and we've got a positive and a negative frequency. So there is there is this concept of there being a negative frequency and also a positive frequency. Now, you can put the control block on this particular block. There's a whole lot of options that I'll go into in a short while. And you can put in some maximum holds, minimum holds, averaging. Do you want it to auto-scale both the X and Y axis, so you can do all of that sort of stuff? What sort of Fourier fast transform do you want? What the bin size is for that particular Fourier transform? And if you're used to WSJT, where you can play with this stuff, that's actually an option that's available to you in WSJT. You want the free trigger, or do you want to actually set a level so that it only triggers past a certain point, and then you can stop the particular graph? But I just wanted to show you, this is actually giving you this concept, I suppose, that there is both a positive and a negative frequency that you're actually generating here. In most cases, we're in the real world, we're only looking at positive frequencies, but in software-defined radio and fast Fourier transforms, negative frequencies are actually a thing that you actually have to deal with. So anyway, we'll stop this, and we'll head to now another concept. Another concept that I've got written down here. Some blocks enable you to change the sample rate. So in software-defined radio, there is this concept of what they call decimation. Now, decimation means that you can change the sample rate so that you only need to take a certain number of samples to actually end up representing whatever that frequency or that input is. And what that means is you're not having to process a whole lot of data, and your computer needs to be really, really powerful to be able to process it, because what it's doing is only taking the sort of the third or the fourth sample, and it can quite adequately reconstitute that frequency or that particular signal with every fourth sample. So that means that if it's only processing every fourth sample, it's not processing every sample. So that bandwidth can actually, that CPU type bandwidth can actually be used for other modules. So decimation is something that you do so that you can actually reduce the amount of computing power that you actually need as part of this. And one of the rules, I suppose, in GNU radio is if you're doing decimation, do it as close to the source as you actually can, because what that does is then cut down the amount of computing power that you need, and also make sure that when you put a low-pass filter before the decimation, make sure that you actually put that low-pass filter in before you decimate in a particular block, or you have the possibility that you violate Nyquist. Now, Nyquist just says that any processing needs to be twice the frequency to what you actually want output. So you need to just be a little bit careful and put that decimation in if you put in, say, a low-pass filter or the like, because you'll suddenly find, oh, hang on, I'm not actually getting any output, and what that's actually potentially indicating is that you violated Nyquist's law. So there's a few things you've got to watch. Now, exercise 2. Let's move on to exercise 2. There's a lot of concepts in this particular workshop, and we'll get into the really meaty stuff in workshop 3, where we'll put together a whole lot of other blocks. Now, exercise 2 looks very similar to exercise 1. However, if we have a look at exercise 1, there is no transformation block with the float to complex. Basically what we've done is change the output of the signal source to be a real output and a real input. Still need the throttle and straight into the signal source. Now, if we execute this, so we'll execute the flow graph, and it goes away and compiles it, and guess what? we only have a positive frequency represented here. So it just shows you that in doing that transformation, what we've done is, if we take that transformation step out and only deal with the complex numbers, then magically we actually do a filter out, and we've only got a 4 kilohertz signal at the amplitude that it's set to here. And just to prove this is a dynamic system, if we double click on this particular signal source block, you can see there's a whole lot of properties in here. The output type, which is right, is the complex. That's the blue output here, complex. It's using the sample rate that's set by the variable sample rate, which is set over here in this block here. The waveform that we want out is a cosine waveform, and the frequency, let's change the frequency to 10 kilohertz. And we apply that, and we do a recompile. And guess what? We've got a frequency output on 10 kilohertz. Haven't changed the amplitude or anything, so that's all the same. And you can notice it's auto-scaled this particular axis. So that's exercise 2, and that's all about frequency generation. So now some of the other, I'll just show you some of the other, the output source here. I'll just move that up and pull this down, because there's a whole bucket load of different configuration items. Now these configuration lines change for each block. It depends on what the function of the block is. But you can see output type, input type in this particular case, input type. You can put a name in there, so you can name these blocks as different things. So if it's the the first IF or the second IF or whatever else, you can actually name them up. Fast Fourier transform size 2048. That's what it defaults to, and the way that it actually shows it is the window type. There's a whole lot in here that you can, and it shows it in different ways. Center frequency, bandwidth, uses the sample rate in this particular code. Doesn't want any grid, doesn't want auto scaling, no averaging. The minimum and maximum scales are there, and that's the X and the Y axis. Number of inputs, you can have multiple inputs into a particular sync. In this particular case, we've only got one because we only need one, but you can have multiple ones and feed them in. Going through advanced, there are a whole lot of things here. Alias, affinity, so aliasing, you can specify buffer sizes, which is, if you've got data flow issues, then you may need to buffer. So you've got the ability to set up buffers and all sorts of stuff. The trigger, it's currently set to free, defaults to free, but you can set it to an actual level, and it triggers and demonstrates and shows only when it goes past those particular thresholds. Configuration, that control panel that was down the right hand side, you can switch that on and off. You can put a legend in there, access labels, etc., and colours, and then documentation. So this is your help file that is against each of these blocks. So you actually get the help file associated with each of the blocks, and it tells you all of those parameters and the things that you've got to do in relation to this particular block. So, and this varies for each block. This is a fairly complex block. You can see there is a input, there is a frequency input, and there is a bandwidth input. So if you wanted to put some control signals, and you can put GUI controls, so graphical user interface controls, where you can specify the frequency, you can specify the bandwidth, and they would input into these particular inputs on this particular block, and then you get a frequency output, so you could then feed that further on. So display it, and also then feed that into other blocks. So this is, and I'm going to stop it here, because we're at the point where we've gone through pretty much all of the fundamental concepts that we actually need to start building. And I'll just show you quickly the exercise 3, which we'll do next time. we actually introduced both the signal and we introduced a noise source. Put it through a low-pass filter with, and we've got a decimation configuration as part of the low-pass filter. We've got an adder here, or a mixer, and then we do a spectrum presentation using the same GUI frequency sync. So we'll do that next time. We gradually add different bits and pieces to this. So we actually put a file, a recorded file into here, so as a particular source. So there's another source for you. We throttle that back. We do a multiplier, etc., etc. So we get up to exercise 5 in this particular case as being a single sideband receiver. And we actually feed a single sideband audio signal into that and see what we get out. And there is an audio sync out the other side, so we do a bit of filtering on the way through. So it shows you what we're actually, we end up with something that looks a little bit more like I suppose a radio. And one of the other, the more advanced workshops, probably in 4 or 5, I'll actually have a RTL SDR as a signal source, and we'll do some real time decoding of DVB-T signals that we're actually putting out as part of this DATV 9. Too many acronyms is this? Way too many acronyms is this? So that's what next time, low pass filters, noise sources, and modifying blocks, and also a little bit more around negative frequencies. So anyway, that's that. As Mr. Kundell used to say, is your blooming lot for the week. But we've got just a few little. Okay. So, just to finish off, a few reminders. Next week, we have a DATV night, but it is a bit of a hands-on night. The hands-on night is bring along your old monitors, your old LCD monitors, and we will be converting them to LED light panels. We've had Ron Cullen is a bit of a guru expert in this particular area, and so he'll be showing us. You don't have to bring the LED strips. We'll supply the strips. We've got some really nice thin ones that can fit any sort of monitor, but we'll show you how to take it apart safely, how to remove the bits and pieces that you don't need, and then how to convert them into lighting panels. So that's next week, and we'll have a whole bunch of them here that Ron's saving up that we can convert to LED light panels. So if you're interested in that, come along. It's a hands-on. What we might do is actually have, I don't know, a camera set up out in the club rooms, and we'll show the different bits and pieces that we're actually doing. So that's next week. Reminder that the second annual YouTube HamFest for 2021 and Hayden and HamRadio DX is participating in that particular HamFest, and it happens on May 20th, 8th to 30th, so the whole weekend. So take a look at that. It's happening on YouTube. Lots and lots of activities, lots and lots of interviews, lots and lots of things going on. May 28th to 30th. Our June presentation night, which is Wednesday the 2nd of June, is by Mike Hawkins, VK7DMH, on satellite communications and antennas, and he will actually be demonstrating some decodes from satellites weather satellites that will be heading over. May or may not work. Depends on what's going over at the time, but we'll see. Our July presentation night, hopefully, is the Tas Government Radio Network. We're getting Andrew VK7 Alpha Juliet, AJ, up to give us a bit of a view of what's going in the Tas Government Radio Network, the P25 new network. And then in August, we've got a bit of a focus on contesting with Martin VK7GN, on HF contesting and our very own Tricky VK7ZBX on VHF and above contesting. So, and that will be happening about a week or two before the Remembrance Day contest. So this is to get everybody all excited about contesting. So there you go. Our videos for our RF viewers tonight, we've got the YouTube Hamfest promo to start off with. So that's a bit of a funny little promo, which is really good. Mike Groth's VK7MJ's Listening to the Earth, which is our presentation from last week for those who missed it. And then a couple on Antarctica and life in Antarctica, and also Mother's Day in Antarctica, which was a great little video that was released for Mother's Day. And I think we'll probably be at the end by about then. So anyway, that's our ATV night for tonight. If there are any questions, then please shoot them through on the chat channel or on R2, which I'm just switching on. And so that's our ATV night for tonight. Hope you've got something out of it, and we continue on with the GNU radio stuff in a fortnight's time with workshop number 3. This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV night, and we'll catch you next time, 73.